I want to compare the electrical circuits used in two different microphones. On the left is a Rode microphone, on the right is a Neumann microphone. The Rode NT1 is a $300 microphone, and on the right is a $1,100 microphone, the TLM103. I found schematics for both of these microphones, and they are very, very similar with some slight differences, and also definitely differences in construction. So let's take a look at the schematic of the Rode first. This is a schematic of the Rode microphone. The upper section of the schematic is a DC to DC converter, and the bottom section is the amplifier. So let's take a look at the bottom section first, and in fact, let's take a look at the input section. The input is on the far right. It's the XLR connector. The XLR connector has a shield and pins 1, 2, 3. Pins 1 is ground, and pin 2 is the plus signal, and pin 3 is the minus signal. Remember, it's a differential pair. Phantom power also comes in on pins 2 and 3. It's a 48 volt standard, plus or minus 4 volts. But you will have 48 volts available both on pins 2 and pins 3. The preamplifier will have a pull-up resistor to 48 volts at 6.8 kilo ohms. So you can't pull a lot of current with a microphone, but you can steal a little bit of power, certainly enough for a preamp circuit in the microphone. First, we're going to ignore the 2 capacitors and 4 resistors in the center section. That's used for something else. We're going to concentrate on the power input to the microphone. So the phantom power on pins 2 and 3 go through 47K ohm resistors. The phantom power comes in on pins 2 and 3, and there is a small capacitor to ground on these 2 pins. Then the phantom power, shown here on the schematic as 26.3 volts, goes through a 4.7K resistor, and they're then tied together and they go to a 220 microfarad capacitor. So that input 48 volts through a 6.8K resistor and then through a 4.7K resistor gets you a little bit of voltage division. That's probably why they have 26 volts here. And then it goes into a 220 microfarad capacitor to smooth things out. And then it runs into a 15.1 volt Zener diode. And interestingly, it goes through a 100 ohm resistor. Now, I wouldn't have thought to put that 100 ohm resistor where it is, but certainly these guys have had a lot of experience and they know better than I. But Zener diodes can be a little bit noisy and you want to buffer them. There are different ways to do that, but this is what they chose. So we have plus 15 volts available now for the rest of the circuit. And that's the only voltage that will go to the rest of the circuit. Now those 2 capacitors and 4 resistors in the center here are used to output the signal from the preamplifier in the microphone. The plus signal will go through a capacitor and then 2 100 ohm resistors, so 50 ohms. So through a 47 microfarad capacitor and 50 ohms out to pin 2. And then the other side, the negative side, will go through the exact same impedance. It will go through a 47 microfarad capacitor and a 50 ohm resistor out to pin 3. Now some amplifiers will actually have real plus and minus signals. This particular circuit kind of has a fake negative circuit. Actually, it's tied to ground. So ground is the negative side of the equation. Now, if there is common mode, both in the ground and in the plus signal, then it is a differential pair, even though one side is tied to ground. And they chose to have exactly the same matched impedance going to the preamplifier offboard. So let's look at the upper part of the schematic now. Like I said, the upper part of the schematic is a DC to DC converter. It's going to take the 15 volts that we've generated and it's going to bump that up to 73 volts. And it's going to do so with an interesting circuit. The first part of the circuit is built up out of a Schmitt trigger inverter. And the first 2 gates create a 2-phase clock. The resistor and capacitor across U1B, the inverter, creates an oscillator. And that oscillator is set to oscillate at 92 kilohertz, well above the audio range. The signal is fed also to a second inverter. We'll call this a 2-phase clock, phase 1 and phase 2, When one's going up, the other one's going down. The next part of the circuit, the unused gates now on the one package, it's a 6 inverters in one package. So we're going to use 2 inverters tied together and another 2 inverters tied together as buffers, so high current buffers. Phase 1 goes into a pair, phase 2 goes into a pair. Phase 1 and phase 2 now go into a bunch of diodes and capacitors. And I'm not going to go into length about how this works, but you can imagine that since one signal will be high and one signal will be low, if you look at that first capacitor, imagine that phase 1 is low and phase 2 is high. Then the top of that capacitor will be charged to 15 volts. Oh, by the way, the inverter is being run off of 0 to 15 volts, not 0 to 5 volts. It's a CMOS inverter, and it allows you to run that inverter off of a 15 volt supply. So we're swinging between 0 and 15 volts. So if the bottom of that capacitor is at 0 volts, the top of that capacitor will get charged to 15. Then when phase 1 goes to 15 volts, basically the bottom of that capacitor gets pushed up to 15, and the top of that capacitor will then become 30 volts, and that will push through one of those diodes. So you have 15 in, 30 out, and then you have 30 in, and then you're going to add another 15 to that. So you're going to have 15, 30, 45, and then another 15. You're going to get up to 73. Okay, let's take a look at the amplifier section of the schematic. We'll start at the back end. This section should look very, very familiar if you've watched my op-amp series. Q4 and Q5 act as a current source. It's a little bit different than the one that I taught in the op-amp series, but you can think of Q4 as a diode, and the emitter base junction is half a volt. So the base sits at half a volt with respect to the emitter, which is tied to ground. So you have half a volt across the 10K resistor, and that sets up the current. The current then passes through Q5, which buffers it from the rest of the circuit, and you have a current running through the 2 diodes, D4, and through Q1. Q1 is the drive PNP transistor. It drives the output, which is a totem pole configuration, Q2 and a Q6. D4 acts as biasing for Q2 and Q6, so there's no crossover distortion around 0. And the output is at the center between Q2 and Q3. So this circuit amplifies the current. It does not amplify the voltage, but amplifies the current. So we've generated a 73 volts with our DC to DC converter. We want to make sure that it's as clean as possible, that there's no dirt on it from the oscillators and things like that. So the first thing we do is have the 73 volts sitting on a 0.01 microfarad capacitor. And then to clean it up even further, we send it through a 4.7 megohm resistor to 2 capacitors, a 0.1 microfarad capacitor and a 0.01 microfarad capacitor. So why 2 capacitors? Well, these capacitors want to be noise-free at the frequencies you're interested in. And capacitors can self-resonate. They have low impedance only at certain frequencies. So in order to have a very broad band frequency bypass, you use 2 different values, a 0.1 microfarad and a 0.01 microfarad, hopefully making it noise-free over the audible band. So 4.7 meg into those 2 capacitors. And that sets up the voltage that goes into our microphone. So we're charging one of the plates of the microphone to the 73 volts, and it's just sitting there as a DC bias. Now the other side of the capacitor is going to be the part that gives us our signal, the part that we want to amplify. So we send a piece of it over to the JFET. And in some circuits, in some manufacturers, you'll see that that point is extremely critical for leakage currents. Sometimes they put it on a Teflon standoff. In this particular design, it's just on the PC board, but they do put some guard traces around it. So when you do the PC board layout, there are rings around that node to keep any stray capacitance off to a particular value. Imagine that's a little capacitor going from that node to someplace else, to the rings of that guard. And it's kind of like a little capacitor. And as long as the center of the capacitor and the ring of the capacitor are at the same potential, then there's no problem. And so the way that the circuit works is it makes sure that that ring is at the correct potential. That ring is tied to the source of the JFET, and it makes sure that everything is stable. The gate of the FET needs to be biased for that FET to work. And there is self-biasing of JFETs that I'm probably going to talk about in a different video. But in order to get the JFET operating correctly, you need to have a resistor to ground in order to bias that gate. It's called self-biasing. And a lot of times a 1 gigohm resistor is used. You know, many megohms. A lot of microphone preamps will use a 1 gigohm resistor. And in fact, this particular circuit uses a 1 gigohm resistor. Now, that 1 gigohm resistor also runs through a 1 meg resistor to ground, and there's a tap there. That is a really crucial part of the circuit that's really tricky, and so I'll leave that for a little bit later. But just think of this right now as one side of the microphone is a DC, 73 volts. The other side of the microphone goes through a 1 gigohm resistor to ground. So that node goes into the JFET gate, and it's a very, very high impedance, and that's the way we minimize the noise in the circuit. So now we have our condenser element connected to the node, and as sound waves modulate the condenser, it modulates the voltage at that node. So now we have a voltage wiggling at the node. That goes into the gate of a JFET transistor. So the gate is wiggling up and down in voltage. Now, JFET transistors aren't like normal bipolar transistors. What JFET transistors do is they take that wiggle in voltage and convert it to a wiggle in current. So they convert voltage into current. So the JFET transistor will now be wiggling and letting through a little bit more current or a little bit less current. They're almost like a variable resistor. And that wiggle in current then wiggles the base current through the PNP transistor, and that then gets fed to the output section. So that's the way the signal gets through. Before we take a look at the next part of the circuit, we need to go over a concept. Okay, let's talk about these two circuits here. The one on the left is a standard AC amplifier. So the resistors are used to set up DC biasing of the transistor. The capacitors allow AC signal to flow through the circuit. And so it does a good job of sending this signal through the circuit, and the DC biasing sets up the transistor to operate in its best region. Now, one of the problems with a circuit like this is input impedance. The input impedance seen by the AC signal is going to be the parallel combination of those two RB resistors, RB and RB prime. And so it's going to have some input resistance. And if you want to increase that resistance to have a better input impedance, there is a trick called bootstrapping. Now, for people who don't know the word or non-English speakers, bootstrapping is a very old term that comes from an idea where if you are putting on a pair of boots, a lot of times the boots near the heel will have a little loop, a strap, and you can put your finger through that strap and you can pull your boot on, and that's the boot strap. Now, the idea of bootstrapping is that you put your finger in the loop and you pull up and you pick yourself up off the ground. Of course, that's impossible to do, but that's the idea of being bootstrapped, is somehow you magically use something to pull yourself up. And that's what we're going to do here in the circuit on the right. Remember, the input impedance is the parallel combination of those two resistors. So what we've done here is we've added another resistor that ties to that same point. So the DC biasing is still the same. The base of that transistor will still be held at a particular DC voltage. Now the AC signal is going to be a bit different because we've introduced another capacitor, CB. So what CB does is as the AC signal flows through the transistor and appears on the emitter of the transistor, that AC signal will backflow through CB and will modify the DC bias point between those two input resistors. And that value then will be put on the base. So you can imagine that if the signal goes up a little bit, then the DC bias goes up a little bit. If the signal goes down, then the DC bias goes down a little bit. And so the signal going into the device, since you have the DC bias following it, going up and down with itself, you can reduce the input impedance. So this is called bootstrapping. So in our circuit, I think you can see the bootstrap now. There's a transistor that buffers the signal, but the base of the transistor is monitoring the output. That center line through the circuit is the output signal from the push-pull amplifier at the end. And that center wire, this output signal, is going up and down with the audio, and that is buffered through this transistor and sent down to that 1 gig ohm resistor. So the DC bias point of that 1 gig ohm resistor, the bottom of that 1 gig ohm resistor is not ground, it's elevated to a higher voltage, and it's also moved up and down with the signal to reduce any capacitance effects of the JFET transistor. The JFET transistor will have an internal capacitance from gate to drain and gate to source, and so you need to control that because we're talking about very, very low, very, very high impedances and very, very low capacitances. We need to somehow negate those things, and we do it in this circuit with a bootstrap. This schematic shows a typical JFET amplifier with self-biasing. You can see that the gate resistor is placing the gate at 0 volts. Now, I said before that these transistors are kind of odd. They're more like a variable resistor, a variable current source. If you have 0 volts on the gate and 0 volts on the source, so the voltage between the source and the gate is 0, then the transistor will pass the maximum amount of current. So it's basically completely on. And then as you go to negative voltages on the gate, the transistor turns off. Less and less current can be passed until you finally reach what's called the cutoff voltage. So the JFET that we're using in this Rode microphone has a cutoff voltage of about 2.2 volts. So at 0 volts, gate to source, it's fully on. At minus 2.2 volts, it's fully off. And here's the graph of how that's depicted on the data sheet. Now, when you use these devices, you generally want to use them, DC bias them somewhere in the middle. And so if it's fully on at 0 volts and fully off at minus 2.2, let's go ahead and say we're going to bias it so it's at minus 1 volt. And so DC-wise, it's biased at minus 1 volt, and then the AC will pass through. So how do we get minus 1 volt on the gate? Well, we put plus 1 volt on the source. So if we have plus 1 on the source and the gate is at 0, then basically the voltage between the gate and the source is minus 1 volts. Now, to set the source voltage, if you can determine what current you want to operate the device at, and then you can figure out the resistor to use as a source resistor, the source resistor times the current you're going to use will end up being the voltage on the source. So let's say you want to have a 1 milliamp current. You have a 1,000 ohm resistor, and that'll give you a 1 volt source voltage. And then you'll have minus 1 volts at the gate. So remember that bootstrap circuit. It also is doing a different job, which is providing the bias for the JFET. So the output is going to be about midway between 15 volts and ground. And so the output's going to be around 7.5 volts. And that goes over to the source of the JFET, which means if we want the gate to be negatively biased by 1 volt, then instead of 7.5 volts, we want 6.5 volts on the gate. So 6.5 volts on the gate, 7.5 volts on the source. And that's exactly what the simulation he's showing here. The bootstrap voltage is sitting there about, I think he has it at 6.3 volts and the output at 7.3 volts. So a 1 volt, a negative 1 volt bias on the JFET. All right, the final trick to the circuit is that the output is tied directly to the source of the JFET. So instead of being connected to ground or referenced to ground in some sort of way, the source is referenced to the actual output itself. So if you imagine that in our op amp we had a positive input and a negative input, and if we wanted to have feedback and have a unity gain, then the input would be on the plus terminal and the minus terminal would be tied to the output. So that's exactly what's going on here. The JFET gate is acting as the positive input and the JFET source is acting as the negative input. So if you think about this, if the gate goes positive, then the JFET starts to conduct, and that makes the PNP conduct, and that makes the totem pole conduct upward, so things go up. So if input goes up, output goes up. Now the output is fed back around to the source. So that means the source goes up, which means the biasing of the FET is changed and the FET will conduct less. So it's negative feedback. It's a very, very clever way to use the FET in both a plus input and a minus input. This might take some thinking on your part to figure out how this actually all works. But it's a very clever circuit. It's a minimal number of components, and it's doing a lot.